Okay, so this is lecture 13 of 124103, where we will learn about fluid dynamics. So last time in lecture 12, we started to learn about fluids. We really just defined the terms that we need, what a fluid is. We learned what density is, and pressure being related to fluids as well. But in lecture 12, we considered only fluids that are static, meaning they are not flowing, they're not moving. So water in a container, water in a lake, for example. Then we can find the buoyancy force, which allows an object to float or sink. But in this lecture, we will consider fluid flow because fluids, most of the time, they're not really static, right? So the flow of fluids is quite important in many applications. For example, in aerodynamics, you have air being gas fluid, moving around an object. Fluid flow is also important in astronomy with weather patterns and how the atmosphere moves. Most especially fluid flow is important in physiology. So blood flows through veins and arteries. So in many applications, fluid is not really static. So we need to learn about concepts relating to fluids that are flowing. And so that's the topic for today on fluid flow. So when fluid flows, one of the most important things to know is how much fluid is flowing per unit time, right? We want to know how much fluid crosses an area in any given time, and we can relate this to flow rate. So flow rate, this is just the term that we use for how much fluid crosses an area in a given time. When we say how much, we mean volume. So it's the volume of fluid crossing an area per given time. So we'll use the symbol capital Q to designate flow rate. And so when we say rate, when you read the word rate, because you'll be seeing this word quite often moving forward, when you read the word rate, it's always something divided by time. So in the case of flow rate, it's volume divided by time. So the equation, therefore, for flow rate is volume divided by time, or how much referring to volume, the volume of fluid that is crossing an area for a given amount of time. So if we look at the units for flow rates, the unit for volume is meter cube. That's the base unit for volume. And the unit for time is seconds. Right? So therefore, the unit for flow rate will be meters cube per second. Right? And another useful form for flow rate is the area times the speed of the fluid. Because if you think about flow rate, you can also think about it as how fast, it's as shown in this diagram here, how fast the fluid is moving across or through a cross-sectional area A. Right? And so you have two definitions of flow rate: how much, or the volume of fluid crossing an area per unit time, or how fast the fluid is flowing through a cross-sectional area A. So therefore, you have these two definitions for flow rate. What to use, of course, depends on what you know. Right. So ideally, in the most ideal case, the fluid is just flowing through a constant cross-sectional area. But in reality, sometimes the cross-sectional area can vary while the fluid flows. And so an example is shown in this figure here. For example, initially, the fluid flows through this larger cross-sectional area, and then it encounters a smaller cross-sectional area. Say, for example, a wide pipe narrowing at some point, then how do we describe the flow rates of the fluid through a pipe with uneven thickness? Okay. Right, the thing to remember is that assuming no fluid is being taken or added away as the fluid passes through the pipe, then whatever comes in on one end, so the amount of fluid coming in, or volume of fluid coming in on one end should be the same volume of fluid coming out the other end, right? Because assuming that no fluid is being added or removed or taken away. So therefore, the flow rate through each of these cross-sectional areas should be the same. So you should have equal flow rates through the larger pipe and the smaller pipe. If we write this in equation form, flow rate is area times the speed. So the area, cross-sectional area, so that's area, meaning it's this cross-sectional area here. The cross-sectional area times the speed should be equal at both areas of the pipe, even if the thickness is not the same. Okay. Okay, this equation, this is an equal sign. So the left side should balance out the right side, which means that if you have a narrower constriction or a smaller cross-sectional area, the fluid should flow faster where the cross-sectional area is smaller. This here is the implication of this equation, where the flow rate through the larger cross-sectional area should be equal to the flow rate through the smaller cross-sectional area. Well, if you think about it logically, it should make sense, right? Because, for example, in this larger area of the pipe, you have a volume of 1 liter. So say you have 1 liter of water in this larger pipe, then the same amount of water should be in this smaller pipe. So you also have 1 liter of water through this smaller pipe, right? Now you have 1 liter of water passing through a larger gate versus 1 liter of water passing through a smaller gate. Okay. If the same amount of water is to pass through the gates at the same amount of time, then the water passing through a smaller gate needs to move faster, right? Whereas water that passes through a larger gate, they can move slower because you have a bigger gate to accommodate the 1 liter of water. Does that make sense? Yeah, right. And so therefore, the smaller the cross section, the bigger the speed, or the faster the flow, the fluid flows through a smaller cross section. Okay. A very good example is, have you been to Hookah Falls? Maybe during the holidays or something, right? So some people haven't been to Hookah Falls. So this is how Hookah Falls looks like in Taupo. So it's quite impressive if you get the chance to go see Hookah Falls. It's like a big, and you can really see how fast water is flowing through this area here. So let me just pause the video at this point. So if you notice here, around here, you have like a wider cross-sectional area, right? So water is flowing through this wider cross-sectional area, and then it encounters this region where you have a narrower cross-sectional area. And notice how the water is quite calm where it's wider and it becomes more turbulent when it's narrower. So the turbulence in the narrower part is because of water moving faster through this narrower part compared to the movement of water through the wider part. So at the wider part, water flows slower, so you have a calmer flow of water, and at the narrower part, the water moves faster. And hence you have like this turbulent flow. In the next lecture, we will learn more about turbulence, but we can observe here the difference in the speed of water flow through the wider part and the narrower part. Right? Okay, so the wider the cross-sectional area, the slower the fluid flows compared to narrower cross-sectional area. Right, so does the concept make sense? At least the concept, right? So let's try to apply the continuity equation and see how to use that to solve a problem. So here you have a pipe. It carries 1,000 liters. The 1,000 liters of water flows through the pipe per minute, and the speed of the water is 2 meters per second. And we want to calculate some quantities here. Right? So we want to calculate the flow rate, the cross-sectional area of the pipe, and the radius of the pipe. And then you have here a follow-up question: what happens if the pipe's radius narrows by 10%? Okay, so let's see how we'll solve these questions here. Let's just dissect first what's given. So 1,000 liters, that's volume, right? Liters is a measure of volume. Per minute, so 1 minute, per minute means 1 minute. This is the time. Okay, so you're sort of given time information in the problem as well. And meters per second, we know this is the unit for speed. Speed V. Cool. Right, so let's solve for the flow rate. So flow rate, we have two equations. It's the amount or the volume of water per unit time, or it's also the how fast water fluid moves across a cross-sectional area. So you have these two equations for flow rates, but you don't know the area. You don't know the cross-sectional area of the pipe is not given. What's given is the volume, the time, and the speed. Right, so then it makes sense to use the first definition for flow rate. 1,000 liters per minute is flowing through the pipe. Right, we said earlier that the unit for flow rate should be meters cubed per second. So that signals you that you need to convert your units, liters to meter cube and minutes to seconds. Right, a useful conversion factor, and this will be very useful for you to put in your formula sheet. Conversion factor is 1 liter equals 10 to the minus 3 cubic meters. Right, so then 1,000 liters, that will be 1,000 times 10 to the minus 3 cubic meters. And then for the time, of course, 1 minute equals 60 seconds. Cool. And then we then just solve using our converted units. That will give us 0.0167 cubic meters per second. Right. Okay. Maybe quite simple, right? Okay, so just be aware of the units in this case. Now, second question, cross-sectional area of the pipe. So cross-sectional area, that only comes into the definition for flow rate, being the speed times or how fast the fluid flows through a cross-sectional area A. We've calculated for the flow rate from before, but we need to find the area. So we need to rearrange the area. The speed is of course given in the information there. So if we rearrange this to isolate A, we can divide both sides by the speed, because we want to isolate area, we need to get rid of speed. Speed is being multiplied to the area. We do the reverse operation for multiplication, which is division. And anyway, any number divided by itself is equal to 1. So V divided by V is equal to 1. But we also have to do the same division on the other side of the equation. So V divided by V is equal to 1. That brings us to area equals Q over V. Okay. Q, we solved that from before. Flow rate is the same, and then speed is given. That gives us a cross-sectional area in meters squared. All right. Cool. Next, the radius of the pipe. So the pipe, we can assume that the pipe is usually cylindrical. What we've solved from before was the cross-sectional area was this, And if you have a cylinder and you cut through it and look at one end, that's the cross-sectional area that we've solved from before. Notice that the cross-sectional area is a circle. So we've solved for the cross-sectional area from before, but the cross-section is a circle. And the circle has a radius r, and that is what we are after in this question. Right. I think we learned before that the area of a circle is pi times radius squared. Yeah. Okay. We've encountered this equation for the area of a circle before. So we need to calculate for r, the radius. We need to rearrange this equation to isolate r. Okay, how do we do the rearranging? It's the same method that we've learned before. You can do the building up and then tearing down procedure. Let's do that. Say you start with the variable you want to isolate, which is the radius. Radius is squared. So that means you need to put an exponent of 2 to have radius squared, right? So once you have radius squared, that's multiplied with pi, so times pi brings you pi times radius squared, which is the area that you're, which is the area. And that brings you to building up the equation, and then you have to just do the reverse. Starting from the area, do the opposite of the last thing you did. You multiplied by pi, so you have to divide by pi. So that's area divided by pi. Right, and then you need to do the reverse operation of exponent 2. What's the reverse operation of exponent 2? It's the square root. So you need to get the square root of this one. So you have square root of a over pi. That leads you to r, which is what we want to isolate. Cool. Good. All right. So then we know the area that was solved from before. And apologies for this. This should be a superscript -3 divided by pi. Get the square root that gives you the radius. All right. Okay. The next one. Say if the radius narrows by 10%, calculate the new speed of the water. Okay, so something new to learn today, percentages. How do we deal with percentages? Right, so we know the radius. The radius we solved from the previous question r. It's this radius that narrows by 10%. Okay, narrows by 10% means that the radius decreases by 10%, right? Yeah, so narrows by 10% means that the radius you've calculated decreases by 10%. So it's 10% of the radius that you've calculated. Now in math speak, 10% off, so 10% percentage means divided by 100. So when we say 10%, that means 10 divided by 100. Okay, and then off, this is multiplication. So in math speak, when we say 10% of something, it means 10 divided by 100 times that number. So when we say 10% of 0.0515, it means 10 divided by 100 times 0.0515. Cool, clear enough? Okay, so that gives you 5.15 times 10 to the minus 3 in meters. So this is how much the pipe narrows in terms of meters if it narrows by 10%. But what is the actual radius after narrowing? The new radius is therefore the original radius minus how much it gets narrowed by. Yeah, so you have the original radius minus the 10% of that original radius. So the new radius is now 0.04635 meters. Yeah.
Can't you just multiply it by 0.9?
Yeah, you can also do that. Yeah. Right. So you've now have the new radius, therefore the new area is calculated using the new radius. And so you have the new area here. What you want to find is the new speed of the water. So we've learned that in the continuity equation, if the air cross-sectional area changes, the speed of flow of the fluid should also change accordingly. So you have there the continuity equation. The flow rate in the old cross-sectional area should be equal to the flow rate in the new cross-sectional area. And we're after this. We're after the new speed in through the new cross-sectional area. So the speed is being multiplied with the cross-sectional area. So like before, if we divide both sides by a new, then we isolate the new speed, right? Yeah, so again, this is a superscript minus 3. And then we are able to find the new speed. So the old speed was 2 meters per second. The old speed was 2 meters per second. The new speed is faster, well, because your new area is smaller because the radius narrowed by 10%. Cool. Any question about this, particularly the percentages, dealing with, yeah, percentages? Good. All right, let's look at another example, maybe a more practical one with related to physiology. So stenosis, this is the narrowing of the blood vessels because of plaque buildup. So if this is a normal artery, so it's not really normal. There's still some plaque over here, but not so much. But in this figure here, there's much more plaque, and so that the area of the artery decreases by 33% because of plaque buildup. By how much will the speed of the blood in the artery increase by? Right, so we know the area decreases, so we know that the speed must increase according to the continuity equation, but by how much is what we're after. All right, again, percentages. Okay. So we know continuity equation says that the flow rate in the normal artery should be equal to the flow rate in the narrowed artery, meaning A1V1 is equal to A2V2. And what we are after is, first we need to figure out what's the new area. And then by figuring out what's in the new area, we can figure out how much the speed will increase. Right, so decreases by 33%. Again, you have these percentages. You can just write it down as these. The new area will be the old area minus the decrease in percentage. So this minus sign here indicates the decrease. This one is, of course, the normal. So the normal. So the normal area decreases by 33%. So then this whole thing is because of the 33% decrease of the normal area. Right, so does this equation make sense? It's like we just wrote down in equation form the information here. So the see, the normal area decreases by 33% of the normal area. Okay, and that will give us the new area. Cool. All right, so carrying out 33 divided by 100, that's 0.33. That's the only thing that changed between these two lines of the equation here. Yeah, simplifying this division, 33 divided by 100. Now notice here you have A1 in this term, and then you also have A1 in this term. So I'll teach you a mathematical trick that can be useful. It's called factorization. Factorization is when you have two or more terms in the equation, and there's a common thing that occurs through each of the terms in the equation. Say here, A1 appears in both terms of the equation. So you can factor out A1, and your equation will look like this. So A1, so factoring out usually takes this form. You have a bracket times whatever is the thing that's common in all of the terms. If you want to check if your factorization is correct, if you have a bracket, that's the same as multiplication. So it's like 1 minus 33 multiplied with A1. And if you're multiplying something with the brackets, you need to multiply that thing to each term in the bracket. So if you multiply A1 to each term of the bracket, you have A1 times 1, that's equal to A1. A1 times 0.33, that's equal to 0.33 times A1. So you can see that you recover your original equation. Okay. So this is your original equation. And this is the factored out equation. Your factored out equation should recover the original equation if you multiply the factor to each term in the bracket. Right. Makes sense?
Is there any reason to put the A1 at the back of the bracket?
No particular reason. It's just that number. It looks prettier when the numbers appear before the letter. But yeah, there's nothing stopping you from putting A1 in front of the bracket. Right? Okay, so after factoring out, we can simplify this. 1 minus 0.33 is 0.67 times A1. Okay, so you now have the new area in terms of the old area. So we can then solve for the new speed by putting in. So this is what we've solved here. We've solved for the new area A2. And we just substitute that to our continuity equation, giving us this equation that contains only A1 and V1 and V2. Right? Okay, what we want to find is V2. V2, that's what we want to find. So we can divide both sides by 0.67 times A1. Yeah, we rearrange this equation, dividing both sides by 0.67 A1. So anything divided by itself, that's equal to 1. And so we're left with V2 on one side. And we have A1 V1 divided by 0.67 A1 on the other side. Right? Okay, so we can simplify this because A1 appears in the numerator and denominator. So A1 divided by A1 is just equal to 1. If we do, therefore, 1 divided by 60, so V2 can be written as 1 divided by 0.67 times V1. Okay, A1 sort of disappears. If you do 1 divided by 67.67, you'll get 1.5. So that means that the new speed is equal to 1.5 times the old speed. Cool. 1.5 times, that means an increase in the speed of 50%. And we can see that 1.5 times something is 50% increase because we can write this down. V2, can you see that space? Maybe I'll use this area. So if we write down this, V2 is equal to 1.5 V1, I can write this as 1 plus 0.5 V1, right? It's the same thing. I just separated 1.5 is written as 1 plus 0.5. So you have this factored form, which you can distribute V1 to each term. So you have V1 plus 0.5 V1. So you can see there that 1.5 and 1.5 times V1 is equivalent to a 50% increase because you have their V1 plus 50% of V1, right? And that's why 1.5 is equal to 50% increase. Cool. All right. Good. All right. So we've learned a few math tricks in this slide, so that's good. So we've seen here so far that the speed will change according to the change in the cross-sectional area, and that's continuity equation. Now let's bring together what we've learned just now and what we've learned in the first lecture by talking about Bernoulli's equation. So in the last lecture, we learned that the pressure will change with depth, right? That's what we learned. The deeper you go, the higher the pressure. So this is this figure here, right? The higher you go, the lower the pressure. The deeper you go, the higher the pressure. This is what we learned from last lecture. What we learned today was that if you have a smaller cross-sectional area, then you have a higher flow velocity or speed. And you have a bigger cross-sectional area, you have a slower speed or lower speed. Okay. We can put these two together in a form called Bernoulli's equation. And this is Bernoulli's equation, this very long equation. And I promise you, this is the longest equation you will encounter in this course. There's anything more, anything longer than this. And each of the terms, So you have two sides of the equal sign. It relates the pressure for a given height to the pressure in another height. It also relates the speed across two sections of pipes. And so each term, the meaning of each variable I've written down here. Just be careful. This is a common, so this is letter P, right? This is letter P, which gives you pressure. This one is the fancy P rho, which gives you density. And this one is pressure. Yeah. In the workshop, we will practice looking at Bernoulli's equation and how one side changes with the other. But in this lecture, I'll emphasize two important special cases for which Bernoulli's equation is quite important. So the first case is when you have static pressure, meaning no flow, but there is elevation change. So how does Bernoulli's equation simplify if there is there's no change in there is no flow, meaning there's no speed, but there is a change in elevation, right? So no flow, meaning the fluid is not flowing, the fluid is just static, it's stationary, therefore speed V1 and V2 should be 0. That means this whole thing. So speed is equal to 0 on both sides of the equation. Anything you multiply with 0 is equal to 0, and therefore Bernoulli's equation will simplify to this P1 plus rho G Y1 is equal to P2 plus rho G Y2. Right. So elevation comes into here. So that's elevation Y1, the height, right? And pressures come in both sides of the equation. So again, this is an equal sign. So it's a balancing equation. What this balancing equation implies is that if the elevation is high, the pressure needs to be low in order to maintain this equal sign. So imagine like if you have, if you increase, this is an equal sign. So if you increase the elevation, you increase this term in the equation, this first term should decrease correspondingly, so that if you add these two, it should equal the number on whatever the number is there on the left. But don't worry so much about the math. The most important thing here is understanding the concept. And the concept is exactly what we learned in the last lecture, wherein the pressure increases with depth, because if you elevate the fluid, the pressure must decrease. So the deeper you go, the higher the pressure, as we have learned in the previous lecture. And in the second case, this is when fluid is flowing, okay, but there is no elevation, a change in elevation. This is this figure here. You have a change in the speed of the fluid, but the fluid flows through the same height or the same elevation. So in this case, Y1 and Y2 are the same. Elevation is the same. And so this whole thing, they're the same. And they're the same thing, and they appear at both sides of the equal sign, so they cancel each other out. And that simplifies Bernoulli's equation to this form. P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Okay. Again, don't worry so much about the form of this equation. All there is to plug in numbers, if anything, but the most important is how to interpret this equation. It's again an equal sign, so we're balancing out the left term with the right term. And what this means is if the speed is large, the pressure must be small. So if you increase the speed, that means this term will increase, and therefore the pressure must decrease in order to keep this right-hand side equal. And this is exactly what we learned. Oh no, it's done. It's a new concept that we're learning just now. So, but if we relate it to what we learned in fluid flow, so if you have here a pipe with a big cross-sectional area, okay, we've learned that the fluid will move slower here. So if you look at the water, let's just say water, so it's easier to visualize. So if you have water molecules here, the water molecules, they're of course moving randomly, but they're moving very slowly. So since they're moving very slowly, they have the opportunity to bump the walls of the container. Okay. And remember that pressure is equal to force over area. So since the water molecules are moving slowly in this wider pipe, then they are able to bump the surface of the pipe, meaning they are able to exert a lot of force on the container or the pipe. And a lot of force means high pressure. And that's why if the water molecules are moving slower, this area of the pipe will have a higher pressure. On the other hand, in the constricted part of the pipe, you have a narrower cross-sectional area. Right? So a narrower cross-sectional area, we've learned that the water molecules should move faster through the narrower cross-sectional area. If you look at the water molecules, they need to move very fast, so though they don't have the opportunity to dawdle about and hit the walls of the pipe or the container. Okay? And since they're just busy flowing through in a straight line, the force they exert on the sides is less, and therefore you have a lower pressure. Does that sort of make sense? How it's all related, like, yeah. Right. Slow movement, high pressure gives high pressure. Fast movement gives low pressure. And this form of Bernoulli's equation is actually quite very interesting. So say, for example, I have a piece of paper here, right? If I blow on top of the paper, what do you think will happen? I blow downwards, but surprisingly, the paper moves upwards. And if I blow faster, so small air speed versus fast air speed, right? In which case did the paper move more? In the second case. Why? Bernoulli's equation, when I blow through the surface of the paper, there is fast movement of air particles above the paper. Fast speed means low pressure. So I create a low pressure area above the paper. So it has a lower pressure compared to the pressure below. So you have low pressure here because of the faster movement of air particles. high pressure below here because the air particles are sort of more static. So high pressure pushes against low pressure and the paper goes up, right? So it's quite interesting. I don't know if you've seen this trick before. So this is just it's a reverse vacuum cleaner because you want to do things in opposite. So I mean, there's air going out. Right, so what's happening there? So this is a reverse vacuum cleaner because instead of sucking in air, it's blowing air out. So it's blowing air out at a fast speed. So air molecules, again, they're moving very fast through this column of air here. What can you say about the pressure in this column compared to the surrounding pressure? So lower pressure where the air molecules are moving faster, and high pressure in the surrounding area. So you have air molecules pushing on the low pressure, high pressure pushing on the low pressure, and that confines the ball where you have high air speed. Yeah. Bernoulli, yeah, that's why this form of Bernoulli's equation is really quite cool, and the implications of it. It also has, so have you ever wondered why in the train tracks you have this yellow line and you're told not to cross the yellow line, especially if there's an incoming train? Yeah, I'm sure you've all observed the yellow line, and this is what might happen. See that buggy? Right, so that's what will happen if you stand beyond the yellow line. Again, you have, so let me pause. Very high speed, right? Fast or high speed that creates low pressure. Okay, and around here you have high pressure. Okay, slow speed or sometimes static air. Right, you have high pressure will push whatever is here towards the low pressure area, and and in trains they're really very fast, and so the pressure here would really be very low compared to the pressure here, and you can really be sucked in if you're not careful, right? It's the same concept with why sometimes it's be careful when you're passing trucks, right? You're overtaking trucks. Again, here between these two, the car and the truck, you have a high speed. So you have high speed of the air molecules. So you have low pressure area there, and you have a high pressure area over here. And this is also why ships collide in the ocean. You might wonder, the ocean is so wide. How come ships collide? It's because if they don't give enough space between themselves, then high pressure will on the other opposite ends of them can push them towards each other. And also it's the same concept again when you're passing a cyclist on the road. Give sufficient distance, because the low pressure that you create when you pass the cyclist could suck them into the road. All right, cool. It's interesting, eh? Bernoulli's equation is really interesting. So just to wrap things off and just put everything together. So we have here a figure of a pipe. You have different cross-sectional areas. Pipe B and D have the same cross-sectional area and they're the narrowest. Pipe A has the next narrower cross-sectional area and the widest, cross-sectional area has a wider cross-sectional area than B and D, and the widest is C. How do we relate the flow rate, the cross-sectional area, speed, and pressure in each of the pipes? Flow rate is the same regardless of cross-sectional area. It's the same amount of fluid passing through each cross-sectional area. Of course, cross-sectional area, you can just see from here which one has the smallest cross-sectional area and the biggest. Now, the speed, okay, this will be continuity equation, right? So through which area will you have the lowest speed? C, right? And the highest speed will be B and D. Cool. And so in terms of pressure, which area will have the lowest pressure? Yeah, where you have slow speed, that's where you have low pressure. I'm sorry, high speed is where you have low pressure. Cool. Good. And so that wraps up our discussion on fluid dynamics. So we assumed that there's no friction. In the next lecture, we will see what happens if there is friction in the fluid. And so I'll see you in the workshop tomorrow, and have a good day, everyone. Oh, there's no lab today, right? So there's no, yeah. But in the tomorrow, if you belong to the Friday group, you have labs tomorrow, but no labs today. You're welcome.